Hi, my name is Manuel Titos. I am a postdoctoral researcher in the Department of Signal Processing in the University of Granada. And in this talk, we are going to go through the machine learning basics. The talk has three parts. In the first one, we are going to go through the machine learning concepts, why it is important, why it's needed. Then we will go through the learning algorithms and we will review the most important concept behind them. And finally, in the third part, we will analyze the most important algorithm related with supervised and unsupervised approaches. According with the definition, machine learning is a field of artificial intelligence that enable computing to learn from data and improve their performance over time. So the goal of this field of knowledge is analyze and interpret complex data, leading us to discover instincts that they are challenging using traditional methods. The thing is, to do that, we need a set of data, computational research, and domain knowledge. Here we have a real case where machine learning gets useful in geoscience. In 2021, the Reykjanes Peninsula volcano in Iceland erupted. In this scenario, population downwind was exposed to low air quality conditions, and the scientific community started to run numerical models and classical algorithms in order to infer the gas and smoke dispersion in the atmosphere. However, the results were poor. And then the scientific community started to think to apply machine learning in order to improve this concentration forecast. As you know, to run numerical model, you need to know the eruption source parameters. However, infer these source parameters are so difficult. Then, people start to think how to apply machine learning to infer them. The idea is having the meteorological dataset and having plume height and concentration data series, we can infer the source parameter to introduce them as input in the numerical model and then get the concentration hazard maps. This is how one of the work package of the European project DTGeo born. So, as we see in the introduction, the meaning of learning has different concepts that need to be properly understood. The first one is the meaning of task. In machine learning, the task means the problem that the model needs to solve. For example, classifying image, detection anomalies, or predicting values. So, the meaning of learning itself is not the task. That means that learning is the ability to perform the task. It is a very important concept that we need to remind before to go ahead. Here, in this image, we can see the difference between the task and the learning process. So, as you can see, the task is the objective and the learning process is the way to get the objective. Then, depending on the task or depending on the objective that we are looking for, the machine learning can be clusterized in different kind of algorithms depending on that task. For example, unsupervised learning, supervised learning, or reinforcement learning, where in each different machine learning approach we will have different kind of learning algorithms and different kind of task. The second important concept is the performance. The performance is a quantitative measure or metric to assess the capabilities of the machine learning algorithms to solve the task. As we can see in the figure, for different tasks, for example, regression, where we are going to predict values, classification, where we are going to classify different images, clustering, where we are going to find different patterns inside the data, we will have different metric performance. So typically the performance is used in the test set where the model never see the data before. That means we evaluate the performance of the model in an unseen data set. So then, depending of the value of this performance, we will decide if the model is enough trained or the model needs to be trained more. As you can see in this figure, the performance is affected by different factors. The first one is the domain knowledge or the initial background. The second one is the type of training or kind of training. And the third one is the learning itself. So depending of the task and depending of the knowledge of the domain, researchers can create different input, helping the algorithm to learn and then improving the performance. Regarding the type of training, researchers can also choose the kind of algorithms or kind of learning algorithms to train the model and then improve also the performance. This is why these three pillars are so important to get good performance and to get good trained algorithm. The third most important concept is the experience. As we said before, machine learning algorithm learns from a set of examples. This example reflects the knowledge of the problem, the experience in the problem. So, depending on that experience, we will have different kind of machine learning algorithm. For example, depending on the experience, we will have unsupervised if we don't have label related with our example, or supervised algorithm if our experience have related label. An important thing related with experience is the no free lunch theorem. That means that there is no dataset or experience able to work well for all the scenarios. That means there is no experience or dataset able to get general purpose algorithms. So if one algorithm works well in a specific domain, that means that this algorithm cannot work well in other general purpose scenarios. As we said before, the most famous learning paradigm in machine learning are supervised and unsupervised learning. In supervised learning, the experience, that means the set of examples reflecting the knowledge of the problem, contain both feature and associated label. So the objective in supervised learning is predicts the label or target given the input vector of feature. That means estimating the probability of I given X. As we can see here in the figure, the training dataset, the training data, has different feature or input vector, and for each one we have a label. So then the objective is to predict the correct label. So having the difference between the prediction and the real label, we can train the machine learning algorithms. In unsupervised learning, the experience or set of examples only contain feature. There is no label associated with them. So that means that the objective of the algorithms is to learn useful properties in the structure of the data. For example, learn the probability distribution in order to get different pattern or important information, helping us, for example, to cluster or classify them. As we can see here in the figure, the dataset only contains feature. There is no label. They are hide. But the objective is given the data, find different structure on the data, helping us to cluster them. Nowadays, there is another interesting learning paradigm known like a semi-supervised learning. In this case, the experience or set of examples contain both a small amount of labeled data as well as a large amount of unlabeled data. So the idea is use the small labeled data set to label the large amount of unlabeled data. As we can see here in the figure, we start from small labeled data set. Then we fit or set up a preliminary classifier. Then uses this classifier, we can label large amount of unlabeled data. So using these pseudo labels, we can improve the preliminary classifier using both the small and large amount of labeled data. Finally, to properly understand the idea behind the learning algorithm, we need to understand the overfitting, underfitting concepts. Before to do that, we need to understand what is the meaning of generalization. As we said before, when we train a machine learning models, we want to maximize the performance of the model. That means we want to reduce the error in the training set. This is no like optimization process. However, the objective of the machine learning algorithm is perform well on new and previously unseen inputs. So that means that the performance on the model, on the test set, should be also good. So the idea is to minimize the error in the test sets. This is the generalization concepts. So there are two factors determining how well a machine learning algorithm is trained. The first one is make the training error small, and the second one is minimize the gap between the training and test error. These two factors correspond with underfitting and overfitting. As you can see here in the figure, the underfitting scenario happens when the model is not able to obtain a good training error in the training set. So the overfitting happens when the training error gets almost zero and then the generalization error increase. So basically we can say that the optimum point where we need to stop the training should be when the generalization loss obtained in the test set start to increase. In the meantime, the training loss is decreasing. The key concept to understand the meaning of overfitting and underfitting is the capacity of the model. The model capacity is the ability of the model to fit a wide variety of functions. For example, models with low capacity can have problems to fit the training set. In contrast, models with high capacity can easily overfit because they tend to memorize the properties of the data. As we can see here in the figure, when we use polynomials with different degrees, we can underfit, properly fit, and underfit the true function. So the way to control the capacity of the learning algorithm is by choosing the hypothesis space. That means the set of functions that the learning algorithm allow to use as part of the solution. The most famous technique used to prevent models from overfitting is regularization. Based on the approach used to overcome such overfitting, we can classify the regularization technique into three categories. Those modifying loss function, that means added a penalty in the loss function. The second, modifying sampling methods, so they modify the experience, that means the set of example, including new example, to have more instant to fit the set of parameters using K-fold cross-validation. And finally, those modifying the training algorithm, for example, introducing dropout or early stopping approaches. We will go through them right now. Common regularization methods related with loss function include L2 and L1 regularization. So basically, the regularization methods based on loss function, as we said before, modify the loss function taking into account the norm of the parameter of the model. Looking the figure here, we can see how the loss function has two parts. In the first one, we have the loss function related with the error of the model. In the second part, we have the regularization term. In the case of L2 regularization, the loss include the weight L2 norm of the parameter being optimized. So the idea behind L2 regularization is to avoid large values for the parameter being optimized, then reducing the amount of function describing the distribution of the data. For L2 regularization, the idea is to use just the L1 norm of the parameter, so then they tend to have sparse values. So the idea is to reduce the number of parameters being considered to describe the distribution of the data. Regarding regularization method related with sampling, the idea is to manipulate the amount of data in order to create a new representation of the actual input distribution, having more examples. So if we look the figure, the most important methods are data augmentation and cross-validation. In the first one, in data augmentation, we have, for example, an original image, and then we can create a new representation using rotation, flip, scaling, or changing the brightness of the image in order to increase the amount of the data set. In the second, in the cross-validation, we will have different partition of the data where we have test and training set in different ways in order to train different model and then average the performance. Finally, we will find regularization term related with the training algorithm. The most important ones are dropout, mainly used in neural network, and early stopping. Dropout include the dropout of different neurons in the network, then alleviating the number of parameters describing the data. In the early stopping, the idea is to stop the training when the lost training decrease, meanwhile the generalization training increase. Mainly the early stopping take values around 10 or 15 epochs. So that means during training, if after 10 or 15 epochs the training loss and validation loss diverge, the training will stop. Here you can see a real example where early stopping gets useful. The idea is to classify volcanoseismic signals. So then, in the top of the figure, we can see the general workflow to parameterize them. The idea is to create different frames, where each frame is parameterized using a logarithm scale filter bank, and each frame has a label. We then trained two different machine learning algorithms. The first one is the dilated recurrent neural network, and in the second one is the temporal convolutional network. As you can see in the figure, the training and test lost diverge after a few training epochs. In the dilated case, around the epoch number 75, the training and test loss start to diverge. Then the early stopping stop the training of the model, and then the parameter of the trained model take the values on that epoch. In the right side, when we are talking about temporal convolutional network, the early stopping acts around epoch number 40, when again the test and training start to diverge. Why this is important? Because if we look again to the left side in the dilated version, we can see how we can keep training the network long time, and then we never find a good point to stop the training. In the second example, in the temporal convolutional network, it's more easy to see that after the epoch number 40, the model gets poor trained. In the first parts of this talk, we were talking about the basics of machine learning, and we were through the most important concepts and learning algorithms. In this second part, we are going to go through some of the most famous supervised learning algorithms, as well as most of the most famous unsupervised one. As a summary for the first part, we can say that machine learning algorithms can be categorized depending on the task, but also depending on the kind of experience they are allowed to have during the learning process. In addition, I would like to highlight the no freelance theorem. It states that no single method is best for solving all problems. The model working well in one case may fall in another. So depending on our data, we will have general purpose or high specialized algorithms. As we said before, supervised learning relies on leveled data, where each input has a corresponding output, allowing the model to learn from example. The idea is to learn to predict the output given the input, that is, estimating the probability of the output given the input. We can do that using maximum likelihood estimation, for example. The list of most common algorithms or supervised algorithm is big, but the most famous one could be neural network, random forest, support vector machines, linear regressors, decision trees, etc. In this talk, we are going to focus on neural network and random forest. The random forest is one of the most flexible and easy to use supervised algorithms. It combines the output of multiple decision trees to reach the results. As you can see in the figure, the idea is split the training set in different subsets, then train different decision trees in each subset, and then average the vote for all the decision trees to get the prediction. This is the concept of forest. That means builds an example of decision trees, usually trained with debugging methods. The general idea of debugging method is that a combination of learning model increases the overall results. The random forest is one of the most robust learning algorithms because it presents several advantages. For example, not all trees are the same. That means each tree has a unique attribute, variety, and feature concerning other trees. We can easily parallelize the computation. That means we can use all the computational results to build random forest, since each tree is created differently from different data and feature. And one of the most important is the stability, since the final result is based on varying, as we said before, meaning the result is based on majority voting or average. As a disadvantage, we need to highlight that random forests have some problem when they need to extrapolate data. And also, random forest does not produce good result when the data is sparse. Other of the most important supervised algorithms are the artificial neural network. They are efficient computing systems inspired on the human brain. They consist of a layer of interconnected neurons or hidden units that process data and learn patterns. As we can see in the figure on the left, the input layer receives the raw data. Then, the hidden layers perform calculation and extract feature using weighted connection and activation function. At the end, the output layer produces the final prediction or classification. Looking to the right, in the zoomed vision of the neuron, we can see how each neuron receives multiple inputs depending on the number of features from the previous layer. Then, each feature or each input has a weight that determines its importance. Then, the neuron adds the weighted inputs to get the results. The results pass through an activation function to decide the output. At the end, the neuron sends the process value, the output, to the next layer in the next word. During training, the weights and bias are fixed or adjusted to improve the model's accuracy using algorithms like backpropagation. So then, we can say that the goal of the artificial neural network is to learn the values of the parameter theta that result in the best function approximation describing the task. So, another important conclusion about the neural network is that with at least one hidden layer and considering a bigger amount of hidden units, they can be seen as universal approximator. So we can approximate any function using just one hidden layer and enough hidden units in this hidden layer. Well, we can also say that the capacity of the neural network can increase if we include more hidden units and layers, but they easily tend to overfit. So, as a summary, we can say that training an artificial neural network means find the weight or the parameter able to minimize the function to solve the task. So basically, to do that, people use some optimization process like gradient descent. Then, the key idea when training an artificial neural network is that we are trying to solve a non-convex optimization problem. That means we can run into many local minima or optima during the training process. If we look into the figure, we can see how the loss function can run into many local optima during training. So then we need to include learning rate in the learning process when we are updating the values of the parameter to jump between different local minima. Finally, for preventing overfitting when training artificial neural network, people used to include different regularization techniques. One of them is limit the number of hidden units per layer. Another one is limit the size of the weight. The first one should be early stopping criteria. And finally, people used to apply dropout, where the rates range between 5 and 15% of the neuron. Regarding unsupervised learning, as we said before, the dataset only contains feature. There is no label associated with that feature. And then the objective is to learn useful properties in the structure of the data. One of the most famous tasks in supervised learning is the clustering of the data. The idea is to cluster the data in different groups, describing different properties for each group. Similar to the supervised ones, we can have different unsupervised algorithms. But between them, the most famous ones are k-means, autoencoders, generative adversarial networks, principal component analysis, etc. In this talk, we will focus on autoencoders. They are a specific version of artificial neural network trained in an unsupervised way. As we already said, the autoencoder is a kind of artificial neural network used to learn data encoding in an unsupervised way. The goal is to learn a lower dimensional representation, known like encoding, for higher dimensional data. Typically, autoencoders are used for dimensionality reduction and clustering tasks because they are able to capture the most important feature in the input. The structure of the autoencoder consists of three parts. On the left, we have the encoder. In the middle, we have the latent feature. And on the right, we have the decoder. The encoder compresses the data into an encoded representation. Typically, this encoded representation is several orders of magnitude smaller than the input. This encoded representation is known like a latent feature. Then, the decoder decompresses the latent feature and reconstructs the data back. When trained the autoencoder, the output of the decoder are compared with the ground truth, and then we minimize or optimize the parameter, minimizing the loss function. As we already said, the key idea behind the training of autoencoder is the reconstruction loss. This loss measures the difference between the input and the reconstructed output. The training process penalizes the network or the parameter of the network when the reconstructed output deviates from the original input. Most of the loss function, or most of the typical loss function for training autoencoder are mean square error, binary cross entropy, and categorical cross entropy. Finally, it is important to highlight that there are many types of autoencoder depending on the specific task to be solved. Here in this talk, we are going to focus on the denoising version. However, it's important to highlight too that the variational autoencoder are getting useful in generative modeling. Here, in the figure, we can see the structure of the denoising autoencoders. As we can see, the denoising autoencoder is a type of autoencoder designed to remove noise from data and improve feature learning. The model receives an input that has been intentionally corrupted with noise. Then, the encoder compresses the noisy input into a lower dimensional representation. Finally, the decoder reconstructs the original, clean version of the input from the compressed representation. This kind of autoencoder is helpful in noise reduction, in feature extraction scenarios, and when we try to train deep neural network under a pre-training paradigm. This slide presents the reference used for these introductory talks. I encourage students to review them in depth, as they provide valuable information to expand their knowledge on the topic. If you have any question, please contact me. Thank you for listening to me, and I hope see you soon.